Welcome to SPIT.
I'm Akshat Deshmukh,
I am Chaitanya.
I am Tejashri.
and we are second year HCC students at SPIT, and we are here to present the MSIC project.
The analog kick drum.
Watch till the end and vibe with the beat.
Let's see how it works. Using a 555 timer IC, we are able to generate a 5 Hertz square wave, and instead of using a function generator, we are generating our own function.
So this is the distortion knob. When we vary it, the distortions will be added. This is the decay knob. When we change the tone, this one is the pitch. What is the pitch? When we vary it. This one is the tune decay. When we vary it, then the is the tune depth. And this one is the pitch shift.
So here we present an audio amplifier using LM386. So the use of this is it not only amplifies the volume of the drum, but it also controls the volume of the output. So let's check it out. So when I reduce the volume, even as you can see, the waves have died away, and even the voice has stopped. So that's the circuit. That's what. Now let's look at the design of the circuit. This analog kick drum synthesizer is inspired by classic drum machines like the Roland TR-808 released in the 1980s. But before we move on to the simulation, first let's define the objective of this project and the block diagram of this circuit. So the objective of this circuit is to generate a repeating kick drum sound using a combination of trigger sequencing, analog sound synthesis, and audio amplification. Now, traditionally, if we look about generating this sound, this is what it looks like. Envelope, VCA, VCO, it's a lot of it. It's too complex. But avoiding all that complexity, we took inspiration from Roland TR-808, and they used some really innovative and cool hacks to tackle these problems. So let's look at it. So this is the block diagram, and this is the block. These are the blocks. As you can see, there is trigger block, accent CV controller, pitch envelope, bridge T oscillator, which is the heart of the circuit. There is a decay and pitch modulator, tone and distortion, and amplifier. You might have guessed how each of them are interconnected. So I'll show you that. So this is it. And if we talk about input and output, the input goes into trigger, the output comes out of the amplifier. So now you are looking at the simulation. This simulation is done on fullstart.com, which is a very easy platform for doing online web-based simulations. You can easily share those simulations with your friends or colleagues and work as a team. So let's start with the explanation. So if I zoom in, okay, so this is the complete circuit, right? If I zoom in onto this block, this block is the sequencer block. As you can see, you might have identified that this is a timer IC. The sequencer, I'll call it sequencer. The sequencer generates periodic gate pulses that define the rhythm of the kick drum. So this section mainly consists of a timer IC in stable multi-vibrator mode, and the frequency of the signal is adjusted by 50K potentiometer, which we have used in our main circuit on the breadboard implementation. And this allows us to vary the frequency from 2 Hz to 6 Hz. So here, instead of using a potentiometer, I've just used a resistor and it gives out a fixed frequency. But in the breadboard implementation, we have also used a potentiometer in series with this, and so that we can vary the frequency as per our requirement. The output varies from 0 volts to 10 volts with a duty cycle of approximately 40%. Now, to tackle this problem, we have also used a 414 fast switching diode in parallel with this 22K resistor so that the duty cycle remains constant, somewhat remains constant. Now, if we directly feed these long gate signals into the kick drum circuit, we get two kick hits, and one when the gate goes high and the other when it goes low. So we need another circuit to solve this. So here we go. This is that block. This block converts long gate signals into very short trigger pulses. It consists of a high pass RC filter and an op-amp comparator. When a gate pulse enters the capacitor, a short voltage spike is generated. The comparator detects this spike and produces a narrow trigger pulse. This trigger pulse is then sent to the kick drum input. A diode is also added to block negative voltages and prevent unwanted oscillation. This stage is extremely important because it ensures that only a single clean kick is generated per pulse. Now, I'll move slightly ahead to explain you what actually the circuit is based on. This is the bridge T network. This is the heart of the circuit, I'll call. This design is based on a bridge T oscillator, which was inspired by vintage analog drum machines, which is also used in Roland TR-808 and its previous models. Unlike a normal oscillator that continuously generates sound, this oscillator only rings briefly after receiving a trigger pulse. The circuit uses one op-amp, resistors, and capacitors arranged in a feedback network. It's the feedback network. Now, when the trigger pulse reaches the non-inverting input, the op-amp begins oscillating. The oscillation gradually loses energy and dies out naturally, creating the decaying sound of a kick drum, as you can see over here. There's a decaying sound, decay in the waveforms. Now, by carefully selecting the resistor and capacitor values, the oscillation frequency is kept around 50 to 100 Hz. Now, why is this important? Because if you talk about a kick drum, it has got that deep bass. And to generate that deep bass, we need to touch up to frequencies of 100 Hz, 150 Hz, or even lower than that to achieve a very deep voice. So that is why we have chosen these values of resistors and capacitors. Now, the project also includes variable pitch control, variable decay, variable accent control, tone shaping, distortion setting, and other settings like pitch CV and accent CV. These are the potentiometer knobs which actually control it, as we have also seen in the demonstration. Now, to give a brief idea about these circuits, these are some small circuits which tweak the waveform here and there to achieve the desired kick drum effect, giving us a DJ kind of vibe. Now, this modulation is achieved by inserting potentiometers wherever required And you have already seen how the waveforms and audio change by turning their knobs in a demonstration. Now moving ahead, if we come out here at the output side, to explain you the amplification part of the circuit, I'll move to a different software because that pulse start did not contain LM386. So I'll show you MNI Multisim document. Here, as you can see, this is the part where the amplification is happening. Now, why is it actually required? See, the kick drum output signal coming from here is relatively weak and cannot directly drive a speaker, or the output is too faint and weak. So we decided to use a power amplifier IC, which is LM386, and the kick drum output is connected to the amplifier input through a coupling capacitor. And the amplifier increases the signal power and drives an 8 ohm half watt speaker. And this allows the analog kick drum sound to be heard clearly and loudly, as you have seen in the demonstration video. Coming back to Falstad, because in simulation case, we do not actually need that amplification because we can just zoom in on the waveforms. So these are the waveforms which I'm talking about. You can see that there is a spike at the start whenever there is a trigger, and the waveforms keep fading or decay, as I should say, indicating a perfect kick drum kind of sound. And whenever there is a trigger, these waveforms appear, indicating the success of the circuit. So that is the simulation. As I change the frequency of these waveforms appearing will also change. So you can see that initially this was 30K, and now when I made it 10K, the frequency has increased, right? So that is it. That is the simulation. Now, I would like to highlight certain limitations of this circuit. So this circuit is designed specifically for a kick drum voice. So if you're not interested in audio, it might sound a bit monotonous, but it is exciting. Definitely it is exciting, and you should try the circuit by yourself. But yeah, so the range of sounds it can generate is limited. And since the project uses analog oscillators and op-amp feedback networks, the output is sensitive to resistor tolerances and capacitor tolerances. There's limited sound flexibility. It is sensitive to noise. And since we have implemented the circuit on breadboard only, the quality of sound might uh, get down a bit. And also the output power, if I talk about that, we need to amplify the output signal so that the audio is audible clearly and loudly. So these are certain limitations about this circuit, but definitely it's worth it circuit and you should try it at your end. In case you have any doubts, you can put it in the comment section as well. And we will also be sharing this simulation file so you can try it out at your end also.
The timer IC handles rhythm generation while the analog oscillator generates the actual drum sound. So with this project, we understood oscillators, filters, op-amp feedback, trigger generation, analog sound synthesis, and many more things. So that was all about the circuit. I hope you also learned something new today. Thank you and happy learning.